Buenos días a todas y a todos y muchas gracias por estar aquí en nuestro Seminario de Vulcanología. El día de hoy tenemos el gusto de contar con la presencia del doctor Noah Randolph Flagg, que nos va a presentar un seminario titulado Rain Falling on Hot Rock, How Critical Mineral Deposits and Hazards Emerge from Hydrothermal Processes. Antes de empezar, como siempre, voy a leer una pequeña semblanza del Dr. Noah. El Dr. Noah es profesor asistente en el Departamento de Ciencias de la Tierra y del Medio Ambiente de la Universidad del Kentucky, en Estados Unidos. Su investigación se centra en agua subterránea, en los procesos geológicos, y su trabajo suele también enfocarse en modelos numéricos de flujos de fluidos, geoquímica de equilibrio y observaciones en campo. Antes de incorporarse a la Universidad del Kentucky, fue investigador postdoctoral en el Centro de Investigación AMES de la NASA, donde recibió una medalla NASA al logro científico excepcional en el 2023. Obtuvo su doctorado en Ciencias de la Tierra y Planetaria en la Universidad de Berkeley, en California, y obtuvo su licenciatura en Geología en el Charlton College. Dr. Noah, many thanks for being here, and please go ahead with your presentation.
Thank you so much for that kind introduction. Thank you all for being here. Thank you, Marie, for having me. So today I'm just going to be talking about water and rocks, and I was going to sort of talk about two different aspects of that. One is how you end up with mineral deposits, and one about how you end up with hazards. This is a photo. This is me wearing a shirt that says "Person for Scale." This is one of my PhD advisors and Marie's PhD advisor, Steve Self. And these columns are the result of rain falling on hot rocks. And I think the pattern is telling us something about process. So today I'm going to mostly be talking about how we go from patterns and alteration to understanding fundamental things about volcanoes. Before that, I thought maybe I would orient all of this work in the context of critical minerals, which are sources required to build all of these things, solar panels and electric cars. Many of these materials come from the types of processes that we're going to talk about today. Just as context, this is a gas-powered car, and it requires some copper, it requires some manganese, it requires a lot of iron. And then for every gallon of gas it burns, it produces about 8 kilograms of CO2. And as we transition into these electric vehicles, you need this giant, diverse group of weird minerals, things like lithium, rare earths, cobalt. And many of these materials come from hydrothermal systems. When we look at the change in demand from, so this is looking at the increase in demand for these different materials from 2020 to 2040. And you'll see, one, there's a huge increase in demand in all these materials. And finding these deposits has this huge economic potential, particularly for places like Mexico and Kentucky that have these deposits. Finding new deposits also addresses humanitarian and environmental crises. This is where almost all the cobalt in the world comes from. This is a mine in the Congo where many of the laborers are children who have these profound health effects. This is one of the largest nickel mines in the world where they're clear-cutting rainforests, which there's also this sort of national security concern about where exactly these minerals are coming from and how stable the governments of those communities are. And finally, this is looking at the amount of water used for critical minerals as a function of these different minerals. I just want to highlight that when you look at, let's say, lithium, these are Australia, the Altiplano in Chile, China, these are really water-scarce countries. And for every kilogram of lithium that you mine, it requires 1,000 times that much water. You can think about how challenging that is. So hopefully I've talked a little bit about why there's an increased interest in these minerals. And so you would think that we would be better at finding them because there's a lot of interest and effort going that way. And that is the opposite of what is true. So here on the y-axis, we're looking at the exploration effectiveness, dollars spent per dollar found as a function of time. And as time has passed, we've gotten worse and worse at finding these minerals. And I think this is partly because mining geologists are good at their jobs, and they found a lot of the really good mineral deposits that were easy to find. So here on the y-axis, we're looking at depth. X-axis, we're looking at time, and the circles are showing the size of mineral deposits. And so part of the change as time progresses is finding deposits that are not exposed at the surface. And I would argue that in order to do that, there's a technical gap where people want to know, where do we find new deposits? There's also a conceptual gap of how do these deposits form? How can we go from an understanding of volcanic and hydrothermal processes to a prediction about where deposits might form? Okay, so I sort of said this before. Here's all these weird minerals, and most of these are the result of hydrothermal processes. And so this is a video of a black smoker vent in the deep sea. And because I work on hot water, I just rethink of every question as just a hot water question. So where do we find deposits is really a question about where do hydrothermal systems form critical mineral deposits. And how do these deposits form is really asking a question about how these systems evolve over time. Okay, I work on hydrothermal systems which exist in all sorts of settings. This is one of my field sites in eastern Taiwan, where there's water flowing through fault zones, and that can cause them to heat up. And that portion of the lab is really being led by JT and RJ, who's my postdoc. Hydrothermal systems often happen in volcanic settings, and that's what I'm going to be talking about today. This is a video from where I'm from in Hawaii, where there's lava entering the water. But what you'll notice is the explosions are happening from the interactions between the heat. The explosions are happening due to the water and the volumetric expansion of water, and there's sort of an army of undergrads working on that. They also happen, hydrothermal systems we think exist in space. So this is Saturn's moon Enceladus, and I've done a lot of work thinking about what hot springs might look like not on Earth. So this is sort of habitability, how do hot springs affect life? Hazards, how do they affect death? And metals, how do they affect the money? Okay, so to me, the ingredients of a hydrothermal system are you need rock, you need water, you need heat, and that affects both the chemistry and the dynamics. So hopefully the geochemists and the geophysicists have something to latch onto. And I'd argue that these systems are poorly understood and remain poorly understood. And that's partly because they're difficult to directly observe. Like this black smoker is under a bunch of water. They're hot. A lot of the action is happening underground. They blow up. And I'd also say that the study is inherently interdisciplinary. What we're looking at is the combined effect of a bunch of volcanism, hydrology, but also a bunch of biology and chemistry. The reason we're able to see these is because of sort of complex redox chemistry. So today I'm going to talk about how do hydrothermal systems form critical mineral deposits. And I'm going to really focus on this one geologic question, which is how do volcanic rocks cool after eruptions? And I'll talk a little bit about what that means for lithium. I'm going to talk a little bit about what that means for hazards. And I'm going to, I sort of tacked onto that discussion about some of the fieldwork I'm doing starting tomorrow. Okay, so this is a cartoon joking that hydrothermal systems evolve, that these chimneys evolve to eat Santas. And so you can see the little Santas decomposing inside of the hydrothermal vent. And this is actually kind of the opposite. The reason that we eat is because we live on redox chemistry. So we can measure the amount of energy available from a hamburger in terms of calories. And hydrothermal systems are actually producing calories of redox potential. So here we have some basalt and we have some ocean water. And we have hot water that moves through the basalt. And as it moves through the basalt, it strips a bunch of iron out and it reaches chemical equilibrium that is very different than the chemistry of the ocean. That these hot fluids are very different than the ocean. And this is why there's so much biology here, is we can measure for some metabolism the calories coming out of this system. Those are the same calories, this is a delta G measured in calories, that produce mineral deposits. And so the reason we're able to see a black smoker vent is you're precipitating a bunch of iron sulfate. And that iron sulfate has much higher concentrations of iron than the basaltic rock you started with. So there's a question of how you go from a basalt, which has a small percentage of iron, to a brine, which has a lot more iron, to some mineral that has a lot more. There's a very analogous process I think is happening in lithium deposits, as you have a rhyolite and you have fluids flowing through that rhyolite, stripping lithium out, and then eventually you end up with a deposit that people mine. And so this means that deposits are a direct consequence of the initial chemistry and the time temperature history. And you can think about this I think about this as like cooking, right? We have some initial composition, we have some starting point, and then the question of how is the cook time and the temperature is whether that meat ends up as something you can eat. So we think that most lithium deposits come from explosive volcanic eruptions. And so I'm going to be talking about explosive volcanic eruptions that kind of have there are two parts to this. There's these volcanic ash plumes. What you're looking at is mixtures of fragmented magma mixed with air that's rising up because it's hot. And then these mixtures also can become more dense than the atmosphere. And so those move along as pyroclastic density currents. Probably a review for many of you. But what I want to highlight, I'm going to talk about these in a really different way, is that the duration of these hazards relates to their energy and the loss of energy. And that's sort of the overarching concept of this whole talk. So here, I'm going to plot energy versus time, and this is the 1991 eruption of Mount Unzen. Many of you probably know this video. But what I want to highlight is that this pyroclastic density current is converting gravitational potential energy, being up high, and thermal energy, being hot, into kinetic energy. And so that's why it's racing down slope. And as it evolves, it's losing gravitational potential energy, it's losing some thermal energy, it's gaining some thermal energy, and it progresses. So what's going to cause this pyroclastic density current to stop? What energy source is going to change as this propagates? Yeah, I heard it quietly. What's happening as it goes down slope? The slope is changing, and so you're losing that source of gravitational potential energy. And so as the slope starts to stabilize, the flow stops, the wind's going to shift and blow all the ash away, and what you're left with is a deposit. And so this is your deposit, which is still steaming, beautiful. And what I want to talk about today is that it's still steaming. It still has a lot of energy. That deposit's still hot, and it hasn't covered this camera. It hasn't killed all these people. It killed lots of people, but okay. And so these deposits are called ignimbrites. And so this is sort of a schematic. You have some magma chamber, you have a caldera, you have some intracaldera ignimbrite, and you have ignimbrite in an outflow sheet. And this is sort of our source rock. This is our meat. And then what we want to know is what is its cook time and what is its cook temperature. Okay. So to do that, I'm going to be talking about a bunch of different volcanoes and a bunch of different ignimbrites. This is the 1991 eruption of Mount Pinatubo in the Philippines. This is that volcanic plume from that climactic eruption. This is the outflow. These are those outflow sheets. This is the caldera. And this is what that landscape looked like immediately after the eruption. You had beautiful vegetated, you had forests, you had valleys, and it is all blanketed and covered in this hot ash. And the question that we're going to just keep talking about is how long did it take for that ash to become cold, go from being hot and dangerous to cold and safe? And we were talking about this idea of an eruption where we have energy changing as a function of time. We're going to talk about that same idea in the deposit. You have some energy, and what happens to that energy over time? And I just want to highlight that it's a lot of energy. So this is looking at the energy as a function of the erupted volume, and this is looking at the eruption energy for different eruptions. And this is the energy that's trapped in that deposit. So I just want to highlight that much of the energy that would drive a VEI4 exists in a deposit of a VEI5. There's a lot of energy in those deposits. Okay, so the obvious test that you would do is you would go and measure how hot these deposits are after they erupt. And Steve, my mentor, had a student, Ronnie, and I think they were just people were bolder, maybe, or they were really brave, and they just went and stuck thermometers in these hot rocks after the Mount Pinatubo eruption. So he sticks this thermometer in the top of the rock, and it's about 100 degrees C, and goes a little bit deeper, and it's 550 degrees, which is about the eruption temperature. And there's a hypothesis. What do you think is going to happen when they go back? It's going to cool down, right? So there's this testable hypothesis, and there are a lot of papers. Oh, yeah, I guess I'll show the papers. We don't need to talk about the problems with these papers, but the idea is that you have a big stack of hot stuff, and we have ideas about how they should cool. And at first, Ronnie goes back 5 years later, sticks the thermometer in the rock, and it's about 100 degrees C the whole time for the whole distance. So this is looking at temperature versus time, and here we're looking at depth. He sticks the thermometer 7 meters down versus temperature. So at first, this looks like you've gone from 550 degrees to 100 degrees. I want to highlight that at the surface, you haven't cooled, not by a single degree over 5 years. And in fact, there was an exposed sort of core of that eruption, and the core also had not cooled, not by 1 degree over 5 years. They go back 10 years later, and again, the surface was still exactly 100 degrees C. And to understand what happens, I do a lot of computer fluid flow modeling. So here I'm going to show you a bunch of results. But here I'm just have the 1991 ignimbrite. This is just a single 1 meter by 1 meter stack of hot ignimbrite. And I'm just going to allow it to cool from meteoric water infiltration. And to do that, we're going to solve two equations. But the point here, the first equation is just saying that mass does not suddenly appear, that water is not magically arriving from places. And this is, again, the idea that energy is not magically appearing or disappearing. So these are just the two conservation equations. And I'm using the Fortran code hydrotherm, partly because it's extensively validated, it's very efficient. So there's a sort of direction of the group trying to figure out how to make these codes more efficient using AI. But the actual thing that is important about this code is it solves these equations in terms of energy versus pressure as opposed to pressure versus temperature. And that means that the equations are continuous. And so they're much easier to solve for boiling systems. Okay, and the problem here is why is the core of this ignimbrite potentially not cooling? And why is the surface of the ignimbrite not cooling? Okay, so here I'm showing depth on the y-axis, and the x-axis I'm showing time. And the color is showing temperature. And what you see is that the cooling of this ignimbrite is not happening through conduction. It's not happening through this sort of gradual cooling at the top and the bottom, but rather the steam layer that is cooling, this dry, hot core of the ignimbrite, is cooling largely through the infiltration of water. And the reason that this cool layer is stuck to about 100 degrees C is that you have these sort of multi-phase flow, where this is an imaginary thin section of the hot rock where there's some mixture of liquid water and steam. And so that leads to this large isothermal layer at the top and a pretty close to eruption temperature layer at the bottom. I've gotten lots of pushback on that, but it is just like an observation. Okay, so here I'm going to show this, again, in cross-section, this view of you have an eruption, you have some ignimbrite, and then this is showing the sort of structure of that ignimbrite outflow sheet. And I'm going to be showing you some outcrops from right about here. This is in Eastern California, so this is Berkeley, this is the Bishop Tuff. Here's the Caldera Rim. Here's a dam, and so it formed this sort of man-made lake. And the next photos I'm going to show you are right here. Okay, so this is that photo that we started with, and what you'll notice is these columns have a regular spacing, that they're due to a difference in how cemented the ignimbrite is, and so you can see the columns sort of lurking inside of the ash. They have these horizontal contractional joints, which I'm not going to talk about, and that they're exposed and they're so beautiful because of this erosion from a man-made lake. Okay, the only difference between these columns of material and the surrounding rock is that they're cemented by this mineral zeolite. So this is mordanite, this is no mordanite. You can see pumices crossing between those. These are forming in situ due to fluid flow in the ash. And mordanite is just volcanic ash plus water, and you get these sort of long crystal structures. These are SEM images, and that gives the rock more strength. So in some ways, this is pushing the hypothesis down. So years after the eruption, there's some water that's above that hot rock. And the question is, how does that water infiltrate in 2 dimensions? And we had this hypothesis that somehow there's some pattern that's forming in that water infiltrating into the rock. And that's being preserved by the zeolitization, by the precipitation of these minerals. Okay, So I'm going to show you another computer simulation. This is a big 10 by 10 meter chunk of hot ignimbrite. There's no flow on the sides. There's a fixed pressure temperature on the top. And in blue, we're looking at liquid water saturation. In white, we're looking at steam. What you see is this patterning emerges simply by having there be rain on the hot rock. And this pattern is specifically being driven by the boiling pressure. And so here in the dark green, I'm showing the pressure due to boiling, and that there's a resonance between the pressure of boiling and the cooling. This correlates really well with some analytical work done by Fitzgerald and Woods. And Woods and Fitzgerald, they wrote a bunch of papers. They're very similar. But on the y-axis, we're looking at the growth rate. X-axis is looking at the wavelength. And they found that water infiltrating into hot rock is unstable, and that it had some characteristic wavelength on the order of meters. What they also argued is that those wavelengths would not persist through time. And so it's actually very surprising that we see that. Okay, so here I'm just showing a histogram of the number of columns versus the column spacing. And here is sort of a compilation of a whole bunch of different hydrothermal simulations. Where here on the y-axis, we're looking at the depth of that infiltrating water. X-axis, we're looking at different permeabilities. Black, you form no instabilities. Gray, those instabilities sweep along, sort of like was predicted by Woods and Fitzgerald. And in white, you have these stable columnar structures that persist through depth. And this is about the permeability we measure in our rocks. Okay, so we could imagine here we're looking at the saturation depth as a function of time, that this patterning actually ends up being really important. And so the way that people often treat the cooling of volcanic rocks, and maybe you do this in your everyday life, is there's like we think about heat conduction, which is a diffusion equation. And this is how we figure out how long we should cook our turkey or chicken, right? Like we measure its size, and then we can predict its cook time based on the diffusivity. There's another possibility, which is that that these rocks are cooling fully through heat advection. And it's just rainwater seeping into the rock. And we can make a different prediction where the cooling is linearly proportional with time. This is you move that cold water down, that's advection. And then there's reality, which is really messy and complicated. And I just want to highlight, so here there are a whole bunch of different simulations, and you can see that the advance of that front can be slower than conduction, or it can be sort of intermediate between conduction and advection. And that this is just thinking about simulations in 2D. And in the field, what we see is this incredible diversity of structure. Here are these sort of hexagonal cell structures. Okay, this is all very pretty, but I think there are real-world implications. You all live near volcanoes. I'm from a volcano. It really matters which of these lines is right. If a volcanic rock erupts, it matters whether it's going to become cold and stable 10 years after the eruption or 300 years after the eruption. Okay, so we sort of started with this 1D model, and I was showing this sort of what matters about the sort of patterning at the meter scale. I'm going to talk about the patterning at the kilometer scale. So here, I'm going to be showing another simulation. So this is the cooling of, this is how we often model. This is a model I did where we have a magmatic hydrothermal system. Here's a caldera. And you have this gentle cooling history. And I'm going to show you the temperature sort of some hot spring in the caldera. So here on the y-axis, we're looking at temperature. And the x-axis, we're looking at time. And here we have this, this is the influx of all that magmatic heat. And then it slowly cools. And I'm going to, let's see. So what I'm going to be doing is I'm going to just show what happens to that cooling if we incorporate the heat from these erupted rocks. So here I'm including the hot ignimbrite. And what I want to highlight is not only are you starting hotter, but what drives this hydrothermal system is you have a temperature gradient. You have hot magma, and you have cold rock, and that temperature gradient is driving flow. Here you have actually suppressed that temperature gradient, and so you've suppressed the cooling of that magmatic system. And so not only are you starting at much higher temperatures, the cooling is a much longer term process. Okay, so I sort of started with this one hydrothermal process that might be important, which is how do volcanic rocks cool after eruptions? And hopefully I've convinced you that, at least in many cases, they cool through these advancing boiling fronts, that they're not cooling in a dry, conductive way as we maybe would like, and that the temperatures can remain high for a really long time. And I'm going to show you the implications of that. But like, this is not just a feature of models. This is something that we observe. Okay, and I'm just going to quickly talk about how this might matter for the deposition of minerals. I'm going to highlight lithium, partly because there's a lot of demand for lithium for your electric cars. Are you guys able to get the Chinese electric cars here? Oh, so jealous. Okay. This is the largest lithium deposit that we know of in the world. Here's a beautiful caldera. And then here are these incredibly lithium-rich volcanic clays. And we think that probably the process, there's a lot of, this is fairly contentious, but I think probably what's going on is that you have hot water flowing through these ignimbrites, it's stripping the lithium out, and you produce these lithium-rich brines and eventually lithium-rich clays. So one question that people have is how much lithium exists in these rocks to begin with? Do you need some unusual process? Do these rocks need to be really special to produce these high lithium concentrations? So here I'm showing that this is lithium concentration on the y-axis and silica concentration on the x-axis, and you can see that there's a little bit of a range of lithium in different rocks. And McDermott caldera, the source rocks, they are high, but not crazily high. That the lithium in these rhyolites is not insane. And so I guess a question someone might have is, given that there's nothing special about those rhyolites, how would we look for the next large lithium deposit? There are lots of calderas, and I don't think it's feasible to look at all of these. And there are reasons to think that some of those might not be true. But here on the y-axis, we've got lithium concentration, the total lithium concentration in the intracaldera ignimbrite. I'm going to show you all of the lithium concentrations, the total amount of lithium from all of the intracaldera ignimbrites that we have constraints on how much. So here, I'm just showing the mean lithium concentration for all volcanic rocks. This is global demand predicted in 2050. This is the largest deposit. And what I want to just highlight here is that there's lots of lithium in lots of volcanic rocks. If we just filter by ignimbrites, there's a lot more. Lithium is higher in ignimbrites. And if we include the fluid inclusions and melt inclusions, it seems like probably these magmas had a lot more lithium. This is a bunch of Tom Benson's work. Okay, and in the interest of time, I'm going to skip through some of the chemistry, but what I want to highlight quickly is that the reaction rate of rocks is a function of temperature. And so what I'm going to be doing is I'm trying to use the time temperature, the Cook times that we have, and integrate the rate at which lithium comes out of these rhyolite glasses. And I would love to not do the experiments because I'm not a lab chemist, but as far as I can tell, there isn't a lot of good work on these types of on rhyolite interacting with water, and so my technician is doing a bunch of bomb experiments. Okay, but here I'm just going to show the amount of lithium. These are for those intracaldera ignimbrites. This is looking at the amount of lithium as a function of time that's being extracted from those ignimbrites. And the point here is that there's a lot of variation, and that the main thing that is driving the difference in the amount of lithium that would be extracted from these ignimbrites is just how big those ignimbrites are. That this is really a function of the caldera size and the ignimbrite thickness. If we include the effects of these cooling ignimbrites in the caldera, you are changing that cook time. And so you're actually cooking these materials for a lot longer. And I would argue we're changing not only the amplitude of the lithium that you're extracting in those brines, but you're also changing the range of these deposits. That the ignimbrite thickness ends up being really important for that cook time part. And this is, I would argue, a testable hypothesis about how to start thinking about different calderas that might host ignimbrites. What I want to also highlight is I'm not producing a deposit in this. I'm just asking how long was water interacting with these ash flows. And we're looking at a whole bunch of different ignimbrites, and I think there's a whole bunch of stuff that matters. Are those brines preserved? Are they trapped? What is the hydrologic setting? And there's a lot of opportunity to add more nuance there. But I guess the question that I started with was, how does this hydrothermal cooling, and I'd argue this is a largely ignored process, affect lithium deposition? And I'd argue that the hydrothermal circulation from ignimbrite cooling produces large variations in lithium. I'd argue this is a way to explore and guide exploration. Okay, so that's the critical minerals part, and I think that many of you are hazards people, so maybe this next part will feel more hazards. So here, I'm just going to show the effects of having hot rock uphill from you. This is the El Fuego eruption in Guatemala. There was an eruption, and years later, there was a block in ash flow as those hot erupted products became unstable. And we don't know the exact number of casualties, but these are before and after photos, and we think there were about 400 casualties. These aren't casualties from an eruption. They're casualties from having a hot deposit remobilize. And I showed you this figure, is that the way in which fluid flows into these hot rocks is controlled by pressure. What I didn't tell you is that these pressures are really high. So here we're looking at temperature as a function of depth. You just saw this figure. And I'm going to show you the effective stress of the deposit as a function of time. So everything in red is stable, and everything in blue or white is unstable. And so the boiling, the effect of having water boil in these deposits leads to really high pore pressures. And this, I think, is leading to sort of a air hockey-like, that the pore pressure from that steam is lofting and destabilizing these deposits. And this is not just an effect of modeling. This is something that was observed after the 1991 Pinatubo eruption. Yeah, I think all of you are volcanologists. The thing that I'd highlight is I keep talking about Pinatubo. We don't have a lot of ignimbrites that have been observed with modern science where we've been able to, we don't have a lot to go on other than models and this one deposit. The other potential deposit is the 1912 Nova Rupta eruption. And that deposit we think is still hot. It's still cooling 100 years later. Okay, so here's the 1991 ignimbrite. Everything is ignimbrite. And this is this beautiful scarp. You can see these pock marks from hydrothermal explosions. This is from 1994 when that ignimbrite remobilized and flowed downhill. This is that map. Here's the caldera. In blue, we're looking at the ignimbrite from the eruption. These are these mapped zombie flows, these remobilized flows that happened for 10 years after the eruption. This, again, work by Steve and Ronnie. And these are quite long. So this is about 7 kilometers. These are about 7 kilometers downslope from the origin. Okay, and what I want to highlight is these are not lahars. These are not landslides. These are hot. And so they behave like volcanic rocks. What we're looking at here is really the behavior of a bunch of hot ash mixed with hot air. And we get the same processes when you destabilize the slope. I like this photo a lot because you can see the dark is showing liquid water saturation, white is showing steam saturation. So if any of you have seen a fresh pyroclastic flow, this is a photo from immediately after one of these zombie flows in 1992. And this is what a pyroclastic density current looks like when it's fresh. This is not what a zombie flow, this is not what a landslide or a lahar looks like. These are highly gas saturated flows. There's also a strong correlation. Okay, so here I'm showing the plume height of these zombie flows as a function of time. And the height, these black lines, is showing the height that was observed. And what I want to highlight, one, is that these are continuing to move very high into the atmosphere 10 years after the eruption. Here's a photo. And that these plume heights are equivalent, right? For those of you that know volcano explosivity index, like there are 2 ways to define that, based on volume or based on plume height. Based on just plume height, these zombie flows, there's no magmatic system involved, are equivalent to eruptions, large eruptions. This looks like a beautiful eruption. Here's your plume, here's your pyroclastic density current, here's your caldera and magma chamber, right? This is fully plume, this is fully deposit derived. And this is showing in 1992. Okay, and I started with this idea that a lot of the energy from eruption remains in a deposit. And so this is that plot that I showed before. And the question is, how long does that energy stay in the deposit after an eruption? And so I showed you a lot of modeling, and that's sort of ways in which you go from the energy that you start with as a function of time, and it starts to cool. But what I want to highlight is that one reason that these systems stay hot for a long time is that's not the only thing that happens. You're introducing a bunch of water, and that water is introducing energy to the system. So there's the latent heat, but there's also the isentropic volume expansion. This is what powered steam engines and locomotives. My son loves steam trains. And this is the whole idea, is that when you have a bunch of liquid water that suddenly boils in a hot material, you're introducing a lot of energy. And so there's a really high payoff when you remobilize these partially saturated flows for a decade post-eruption. Okay, so here I'm going to show you everything that I've talked about is really normal, right? There's just rain, there's a hot rock. There's nothing unusual here. And here I'm going to show you so these are two deposits. These are two field photos from Mount Pinatubo. And how many of you work on ignimbrites, just a show of hands, or pyroclast explosive eruptions? Okay. I will say, I look at a lot of ignimbrites. I would have a lot of trouble identifying where there's a flow boundary of multiple years in these rocks. Like, you're looking at a stack of ash. It's the same ash, and it was in place by effectively the same process. I think it would be really hard to see that without knowing in the field that these are your boundary layers. They're made out of the same stuff. They're in place by the same stuff. It's really challenging. I'd argue that this is a process that we potentially at layer D, or that's like ebbs and flows of that eruption. Yeah, this is the challenge of interpreting these rocks, is it's really ambiguous. And so, a thing that I would argue is that these eruptions stay hot for a long time, and that they're really challenging to interpret from the rock record. So part of why I'm here in Mexico is that there are similar deposits at La Primavera. So this is drone footage of the outflow sheet of that eruption. And here's the ignimbrite. And here you can see these beautiful zeolitized, this is a wall of zeolitization. And so this is recording some complicated process of how this sheet went from being hot and dangerous to cold and safe. I think this is probably the best preserved place in the world to look at this process. Here's another drone video where you can see these walls and these patterns of zeolitization in those outflow sheets. I think it's really exciting and interesting work. Okay, so I started, and I'll have time for questions, started with this question of how do we find critical mineral deposits? And I would argue that we need a mechanistic understanding of how hydrothermal systems evolve, how they form deposits. And then I had this question, which is, how do volcanic rocks cool after an eruption? And I think they do not cool through conduction. The one thing I want to is they are not cooling dry, that they cool through these slowly advancing boiling fronts, and they keep temperatures high for a long time after eruptions. How do we target lithium exploration? Well, I think the hydrothermal circulation from ignimbrites produces large variations in lithium, and that we can make sort of mechanistic predictions about where to look for that, and other deposits like copper. And how do we forecast hazards from cooling? I think that the cooling history of these rocks pose forecastable hazards for decades. Okay, I just started in Kentucky, and I've really just been following the outcrops and where that work is. And so now I'm in Mexico, and I would love to recruit a PhD student who has some field experience with a master's degree relevant to this. So if any of you have ideas about this, this is the campus. It's really nice. It's in a town not as big as Mexico City, but it's a real city. It's not in the middle of nowhere. And it's really nice. There are good mountains. There are no volcanoes. I want to thank all my colleagues and collaborators who've been involved in this work at all sorts of different places. And thank you so much for your attention and time. And I'll take any questions.
Thanks, Dr. Noah, for your presentation.
Yeah.
Any questions? Some questions for Dr. Noah? ¿Algunas preguntas? Luego vamos a ver también las preguntas en línea.
You're also welcome to email. Yeah.
Thank you for your presentation. You already mentioned a little bit that the meteoric water plays a fundamental role on the cooling and the effect of the intimate cooling, no?
Yeah.
And this suppose also a question about the environmental effects in general, no? For example, an eruption in a dry environmental could be different effects.
Totally.
With respect, could you comment more about this kind of role? Because of course here we have a large difference in the raining.
I think that's right. Yeah, I think that's a really good point. I mean, I'll say a couple things. One is that the cooling rate, because water boils, it produces pressure. And so it's actually really hard for that liquid water to get into the rock because you have these high pressures. So the infiltration rates that we're talking about are sort of like a meter per year. So you can think about what's the rainfall rate here? Potential. Yeah.
It's really, really variable.
Really variable. So at Mount Pinatubo, right, you can see that these zombie flows are modulated by the rainy season. So they happen during the rainy season. But I think that this process, like in the Altiplano, maybe there's not enough water, but I think a lot of places, even deserts, have enough water to produce a lot of these effects. The pressure might diffuse away differently. So I think it does matter if you have like a little drizzle all year versus a big deluge of rain. I didn't talk about this, but a hypothesis that people had, Steve and Ronnie had in the 90s, was that erosion is introducing a lot of gravitational potential energy, and that there are reasons to think that's not the story. You can calculate the amount of energy introduced from the system from you have rain and you erode a little bit, and it's just like not quite enough energy to produce these destabilizing effects in most cases. I think it's a really good question. Also, like, how do lakes, right? That you're forming a big hole in the ground, you're potentially like pooling a bunch of water. So yeah, I think there are a lot of open questions.
Thank you.
Thanks.
Could you comment a bit more on these zombie flows or the triggers? You just mentioned that they usually occur or they are associated with the rainy seasons, but then can you comment a bit more about the trigger effects, please?
Yeah, so I think what's triggering them is you have a bunch of rain, and that rain starts seeping into the rock, and you have a rapid increase in pressure at that boiling front. Exactly how they form and how you get the plume heights, I think is not totally clear. But what is happening and what is fairly clear is that you have a bunch of liquid water that's at 100 degrees C, and it suddenly is mixing with a bunch of ash that's at 500 degrees C, and that causes a huge volume expansion. And so how they propagate up versus down the slope, I think, is unknown. It's not clear to me that you need a rainy season to trigger these effects. I think there are sort of intrinsic properties in how these deposits cool and how those hydrothermal systems form that would produce those destabilizing pressures. But I mean, we really only have this one, we only have this one deposit, this one eruption. If there's a big eruption here, I would love to come and stick some thermometers in. If you've got, keep me in mind.
And then the fuels, kind of sort of say, is that you're saying that the ignimbrite is really steam filled, so it's that reservoir of gas that could just like power up this.
Yeah, so there are two things you need. You have this giant reservoir of heat, which is that dry layer, but you also have some liquid water that's in the top, and I think that the boiling of that liquid water is, when it mixes with the heat and when the pressure drops, can introduce a lot of energy, and energy equivalent to the energy of an actual volcanic eruption.
Thank you.
Yeah, I think one thing that maybe would like to argue is I feel like a lot of volcanologists move on after the rocks are out of the magma chamber, and I think there's a lot of interesting stuff happening afterwards. So, yeah.
Thank you for your talk. I was wondering is there any oxidation factor that we should imply in the lithium?
Yeah, it's a really good question. Yeah, lithium's, so there are three things going. I did something a little bit, I did not produce a lithium deposit, right? I just like asked how much lithium do you strip out of the ash? And so that is, that strongly relates to alkalinity and salinity. The formation of the deposits, we actually can say a little bit more. They're almost always in smectites and not illites. And so that's also very redox dependent. I think it's largely unknown how these deposits form. If you're a geochemist, the ways that we measure the chemistry of rocks, right, is people use XRF. You can't see lithium with XRF. You use SEM. You can't see lithium with SEM. You could look in the XRD of the mineral phases, but they're mostly in clays that look a lot like clays that don't have lithium. So those peaks look really similar. And if you use ICP-MS, you'd often use lithium tetraborate, and so you don't see lithium. So it's actually, I think it's a kind of a blind spot of normal geochemistry techniques. So.
I wanted to ask you also something similar to what Sebastian asked you about the zombie flows. I don't understand how, I mean, some they're very high on that graph you showed us.
They're so high, right?
So how, I mean, I can understand how a small one would occur, but how, like 10 kilometers, that's huge.
It's 20. Yeah, there's
20,
one that
yeah.
almost took down an airplane.
And
it's
was
like a
that
Plinian
only
eruption.
calculated
It's like,
on one?
Yeah. So I mean, one, like I agree. I agree with both of your questions. I think it is I don't know what the answer is. I have some thoughts. One is that we don't know if these are like co-ignimbrite plumes or whether they're plumes from the source. And I think that in order to get that high up, I wonder if they're co-ignimbrite plumes and you're effectively mining the energy of that whole deposit that destabilizes. But still, it's really high. It's high enough to produce climate effects, right? The Hunga-Tonga eruption, right? Like, again, we don't have a lot of large eruptions to go on, but the 1991 eruption produced all these climate effects because it introduced a bunch of sulfur to the atmosphere. These zombie flows don't have a lot of sulfur to introduce for the redox chemistry, right? Like, one reason there isn't like a crazy amount of, that this is driven by meteoric water. You're not getting a lot of influence of those magmatic fluids. And there are reasons to think that. So there's not a lot of sulfur to introduce to the atmosphere. You put a bunch of water in the stratosphere, that has big climate effects. And these systems are probably really wet. But yeah, I mean, I think it would be good to do work to figure out how, like I told you about the cooling and that stuff, but exactly how these flows migrate and how they might entrain fluid, I think it's really interesting. Yeah, thanks. I was hoping that there'd be enough for everyone to like latch on to something, so.
Just a curiosity, okay? You showed the spectacular pictures of the columns in the
Yeah.
no? Okay, this is a pattern that is pervasive in the wall deposits, or the thickness of the ignimbrite can play a role in the construction and building of these different cementation processes?
Yeah, great question. Okay, so for what there are 3 places in the world that we know these types of alteration. At Crater Lake, there are features, and they're also, we think, higher temperature. But okay, wait. Your question though is like, why are they forming in this like beautiful, even pattern there and not anywhere else? I think that that's because they're forming on the edge of a lake, and so I think that the pressure conditions were very stable over time. And I think that in the Valles and at La Primavera, they were forming in these valleys, and so things were much more variable over time. But I think it's an open question. In the modeling we have a constant pressure condition at the top. But I was also just showing you 2D simulations that for those of you that do computer modeling, this is like a nightmare situation. Boiling's really hard. And so doing it in 2D was like, people were surprised that we were able to do that. And doing it in 3D, I think would be very interesting. But like those could be walls in 3D.
Then you mentioned that, of course, the pressure plays a crucial role.
Yeah.
Then intrinsically, the thickness of the deposits.
I think that's right. They're not deep. I mean, the maximum temperatures these might be coming from, well, I don't know. I mean, Wes Hildreth, who did a lot of the work out there, has like had very strong opinions about exactly what was going on. And he thought they were forming that there was 200 meters of ignimbrite that erupted and that this was at exactly 100 meters. Yeah.
Can you show again your picture with the columns, the first picture?
Yeah.
Okay. You can see at the top, again, columns.
Yeah.
So can you explain that, please?
So this is like, these are forming within the ignimbrite. So I think these columns, I think it was Sebastian's question, like how, why are they common here? Like this is partly why we see them here because they're eroded away. There's a welded layer of ignimbrite that was above, and so that's eroded out. But so it is unknown how many of these columns exist and are just not exposed due to weathering. But this whole thing is non-welded ignimbrite, and we see them from about a meter above the fall deposit at the base, all the way to the highest place that we're able to see them, which is here. But there was almost certainly non-welded ignimbrite, some thickness of non-welded ignimbrite above this. And if you believe Wes Hildreth, there was another 50 meters of welded ignimbrite, and then there was another 50 meters of non-welded ignimbrite above that. So,
Okay, thank you.
but the reason they're eroding is because water is flowing on the top. And so in most settings, all you see are the things sort of poking out of the ground. The reason they're so pretty here is because you have this lake that's able to, so this is the rise and fall of the lake, and the wave erosion is what exposes these beautiful, beautiful cavern structures. And they're very ephemeral, they're very delicate. Like these might not exist in 100 years. I mean, the lake might not exist in 100 years. There's no water there. Yeah. Sorry. Yeah.
Well, I have a bit of a cooking question. When do we know when to take out the turkey out of the oven? Or when do we know that the steak is well done? Meaning in lithium extraction, when do we know that it's ready up for grabs?
Yeah, well, the way that we could do it, we don't have a whiteboard here. Okay, the way that we would do it, the way that your cooking time of your turkey or your chicken, right, is you say that chicken has, let's say, well, let's do a big turkey because the math will be easier. Let's say we have a turkey with a 1 meter radius. Okay, so that means that the diffusivity of a turkey is about 10 to the minus 6 meters meters squared per second. Okay, so 10 to the minus 6 meters squared per second, 1. So it's 10 to the 6 seconds, so it would be a few days if you had that large of a turkey. But that's the math that we use for cook time. I would argue that the math that we should use here is you actually need to do all the homework and the hard hydrothermal modeling, and you have to like stress about what the patterns are, which is good for me having a job, but bad for like predicting whether something is going to blow up again. But Nova Rupta erupted in 1912, and those deposits are still somewhat hot. There are reasons to think that the fluids that are coming out of that deposit are not being influenced by magmatic system. There's no change in chemistry, but they're still slightly hot. So the heat's there for a long time.
So the turkey won't be done in a long time, right?
I think the answer for, right, we don't have, right, Pinatubo is not a very large eruption. In the scheme of volcanic eruptions, it's not very large. So for this, I think it's hundreds of years.
Thanks.
And I think it was still erupting. Like, I think these zombie flows may have been forming in these large eruptions, and we just don't see them in the rock record. Yeah. Yeah. And we know it's meteoric water based on the chemistry. Like, thankfully, I didn't do that, but you can look at the oxygen isotopes and stuff. This is cold meteoric water. Yeah.
Yeah, my question is, there's some ignimbrite, big massive ignimbrite in the Chihuahua Desert or West Texas. There's any research done in that area?
On these types of features?
Yeah.
Yeah, I don't think that the features are there. I also say, I mean, there's a bias, which maybe we're all guilty of in different ways, is that, like, I think we want to work on what we specialize in. And I think most people that want to work on an ignimbrite want to look at, like, how you got that eruption to begin with, not necessarily how it cooled. So, but a lot of the cooling features that you see are often high temp or sometimes high temperature. So in Bishop, there are really high temperature fumarolic mounds, and those are 400, 500 degrees C. And I think that's a different thing. I think it is interesting, but I think that is really different than this stuff that's forming at 100 degrees C.
¿Alguna pregunta más? ¿No? Ok. Entonces, antes de agradecer de nuevo al doctor Noa, le recuerdo que el doctor Noa va a estar en la sala Servando de la Cruz el día de hoy a las 4 de la tarde, si alguien está interesado a platicar con él. Thanks, Dr. Noa, for your presentation.
Great. Thank you so much. Thank you all for being here.
Y muchas gracias a todas y a todos por estar presente hoy y todas las personas también que están conectadas en línea. Muchas gracias y nos vemos el 24 de octubre para el otro seminario de vulcanología.